So today we have Jim Stone, who's visiting us from Princeton. Jim started his career here in Canada at Queen's University. He then went on to the University of Illinois. He joined the faculty at the University of Maryland. He had a brief stint at Cambridge before joining the faculty at Princeton, where he is now the chair of the Department of Astrophysical Science. He is known for working on a wide variety of astrophysical topics, primarily simulation-based. He's well known for developing Zeus and Athena, which are widely popular hydrodynamical codes. Today he's going to tell us about radiation MHD simulations of black hole accretion disks.
Thank you, Terry. Always nice to be back in Toronto and CITA, interact with people here again. Today I want to tell you about some work I've been doing the last 5 years or so in collaboration with Shane Davis, another former citizen actually, Kyle Felker, who's a new applied math student at Princeton, in particular Yanfei Zhang, who was a student of mine in the Astrophysical Sciences department, and who's most of what I'm presenting today, he's played a very, very big role in this work. Also Kengo Tomita and Chris White, who have also been at Princeton and contributed a lot to this. And this work is all about radiation MHD simulations of black hole accretion disks. So these are luminous accretion flows where we have to worry about the radiation field. And I want to tell you some of the latest work that we've been doing in trying to understand these flows. So I first want to motivate why we want to study this regime, tell you about the numerical methods that are necessary for doing these kind of problems. And then I'll give you some selection of results from the last 5 years or so. Some new understanding on thermal instability in radiation-dominated disks, a new mechanism for forming corona above accretion disks, and tell you some results from global calculations of these accretion flows. So let me first motivate, and probably this is, in an audience like this, I don't really need to motivate very much. But basically, accretion powers all of the most luminous sources. If it's a supermassive black hole, then we're talking about quasars and active galactic nuclei. If they're stellar mass black holes, then we're talking about X-ray binaries. So accretion onto compact objects like neutron stars and black holes is by far the most efficient mechanism for producing energy in the universe. And so the most luminous sources we see are in these accretion flows around these compact objects. There's various regimes of accretion. There can be very, very underluminous accretion, AGN, where the accretion is from very, very low density plasma. The galactic center is an example of that. We're talking about very luminous sources where they're accreting at Eddington or near Eddington, or perhaps even above Eddington. And we're trying to understand this regime of luminous accretion. So if we want to understand these systems, what do we need to include in the modeling? You know, what's the most important physics that needs to be present? Well, of course, an essential ingredient has to be magnetic fields and magnetohydrodynamics. And that's because we now understand that angular momentum transport in accretion disks is mediated by turbulence driven by the MRI, the magnetorotational instability. And these sources are very hot. They're accreting at high rates, so the plasma is fully ionized. The magnetic field is very well coupled to the plasma, and so the MRI is the dominant source of transport. And we know a lot about the MRI, mostly through simulation, both of global models, where you simulate the entire accretion disk and its evolution and structure, or through so-called local shearing box simulations, where you extract a small little volume of the disk and you solve the equations in that small volume and you try to understand in detail what's occurring in this volume. You can focus all your computational resources on a smaller volume and resolve smaller scales, and so you can learn sort of more local physics from this approach. And I'll talk about both kinds of approaches here. So if you want to model these accretion flows, we know that you're going to need to include MHD. That's crucial. But as I've sort of hinted already, radiation is an equally important part of the story. And that's because it's been known for more than 40 years that in accretion disks around black holes, radiation pressure is the dominant energy density in the flow inside several hundred gravitational radii of the central black hole, if you're accreting at something like Eddington. So if you normalize the luminosity, the accretion rate to the Eddington rate for, it's a very weak dependence on mass, so for stellar or even supermassive black holes, within a few hundred gravitational radii, radiation pressure dominates over gas pressure, and you really need to include it in the dynamics because radiation pressure will change the saturation and nonlinear dynamics of the MRI, can change the global dynamics of the accretion flow itself. So why haven't people done this before? Because it's hard. Including radiation is very, very complicated and very, very challenging. So it's been ignored. People just do non-radiative accretion flows, this talk is about trying to correct that and to include radiation fields in the models. And the radiation isn't just an important dynamical component. There's predictions that it's going to change things qualitatively as well. Again, back 40 years, there was predictions of both viscous and thermal instabilities that will be present in these radiation-dominated accretion flows. Viscous instabilities would mean the disk would break up into rings. The angular momentum transport would occur in an unstable manner such that the disk would accumulate in rings, and m dot would be of various radius, and you would fragment into rings. And this thermal instability predicted that the disk would either collapse to a very, very thin, cool disk or expand and heat up and evaporate, essentially, as a runaway process whenever you have a radiation-dominated disk. But only true if you made the ansatz that the angular momentum transport mechanism is proportional to total pressure through the so-called Shakura-Sunyaev alpha parameter. So we want to know, do these instabilities really exist with the MRI or not? Of course, we know that angular momentum transport in disks is not due to a viscous process due to an alpha viscosity. It's due to MRHD turbulence. And it's not clear at all whether or not these instabilities actually exist with MRHD turbulence. We know for sure that the total stress does not scale with alpha p, and so that can change dramatically these predictions. We want to know whether these instabilities exist.
I don't understand the significance of these instabilities because if I understand correctly, what determines the mass accretion rate is what happens at large radii. So up until you get to 170 gravitational radii, you're dominated by the MRI.
Mm-hmm.
So you brought all the mass to this radius. So once you have that, so this is like the initial condition or the boundary conditions for this condition. So
right.
How sensitive are you to these processes?
Well, it would have observational implications because most of what we see is coming from the inner part of the disk. So if the disk was viscously or thermally unstable, it might introduce variability. It might change the spectral signature of the disk. It might change the observational appearance of the disk. But you're right, the long-term global aspects is determined not just from this inner region, but how the accretion disk is being fed and how matter is being fed in. And so those would be kind of separate questions. If we just want to focus on, say, the inner dynamics and whether or not there's any observational implications that we would see. Okay? So our overall arching motivation are very, very broad. We want to be able to calculate the structure and dynamics of these radiation-dominated accretion flows. We want to study whether or not these thermal or viscous instabilities actually even exist in an MRI-driven turbulence. We want to know about outflows and feedback. We know for sure there's going to be a strong radiation field coming out, but in principle there could be also a strong outflow driven by radiation forces. We'd like to know what fraction of the matter falls in and what fraction comes out in outflows. That's very important for understanding the growth of black holes over cosmic times. It's also very important for understanding AGN feedback in galaxy formation. And finally, there's an awful lot of data that exists on AGN and X-ray binaries. We want to be able to compare that data to our simulations to compute emergent spectra, compute the variability, and see whether or not we can constrain the theoretical models directly using observations. We actually have the radiation field here, so we can make a direct comparison between observations and the calculations. So those are our goals. So we need to solve for this problem. I mentioned radiation magnetohydrodynamics. We need to solve the equations of radiation MHD. So here they are. I won't overwhelm you with too many equations, but I'll try to overwhelm you with these, perhaps. So we have the equations of Euler equations of fluid dynamics and the black equations and terms. We include the effect of magnetic fields through the blue terms and equations. So there is a Maxwell stress in the momentum equation and a Poynting flux in the energy equation and one of Maxwell's equations to evolve the magnetic field. In the ideal MHD limit, it's a fully ionized plasma, so ideal MHD applies. So the electric field is just minus V cross B. We also have to add in a set of terms that capture the radiation material interaction. So there's a radiation force on the plasma, and there's a radiation energy exchange rate, a net heating rate. in the energy equation from the radiation field, and we have to add radiation moment equations that describe the evolution of the radiation field in time, where this capital E is the radiation energy density, F is the flux, and P is the radiation tensor. So essentially we add yet another set of moment equations, fluid equations for the radiation field that have to be solved in concert with the MHD equations to solve this coupled photon particle system. So these are a complicated set of hyperbolic PDEs, and it's taken a while to develop numerical methods that can handle these. And I'll describe some of those methods in a minute. But I would say that the good thing is that we think these equations are complete in the sense that they completely describe the physics of fully ionized accretion flows around black holes. There's no missing subgrid physics that we need to add that are important for some other important problems, like, say, galaxy formation, where you worry about star formation feedback and you worry about AGN feedback. Well, those are processes that you can't resolve in current cosmological simulations, and so you add them as subgrid recipes to your calculations, and there's much debate about what the right subgrid model to use is. Well, here we don't need any subgrid models. We think that we have these equations describe the physics directly. So if we can just solve these equations accurately and do three-dimensional calculations, we should be done. We don't have to worry about varying parameters to model the subgrid physics. So I'd say that is a very positive thing, where we think we have a complete mathematical model, and we, quote, only have to solve these equations accurately, which can still be challenging. Yes?
All the processes to have the same length scale. So you have the size of the cell. The cell has to resolve both the hydrodynamics and the radiation. So
that is correct. I mean, there's many length scales in this problem, and they can be very, very small. And so you need a numerical algorithm that's going to try to, and you're limited by your dynamic range and your resolution. Absolutely, absolutely. There is one thing missing from here, which is that there are actually more variables than equations on this slide. The hydrodynamical equations contain a pressure, a gas pressure. We need some equation for the pressure. Well, that's the equation of state. Typically, we use an ideal gas law. So that closes the moment equations for the fluid sector. However, the radiation field has the same problem. There's three unknowns, energy density, flux, and pressure, and there's only two equations. So we have more unknowns than equations. We don't have an equation of state. We don't have a relationship between pressure and energy density for the radiation field. Many people assume such a closure, so-called Eddington approximation, or perhaps flux limit diffusion, or they might assume something like the M1 closure, which would then close this pressure tensor in terms of the fluxes. Instead, we're going to solve this directly by actually solving the transfer equation to compute what the closure is. The challenge of radiation hydrodynamics is you don't know what the closure is. There's no general closure, and it has to be computed directly, and that's very expensive. So these calculations mostly use a new version of this Athena code I've been working on for a while. It's called Athena++. It's a complete rewrite into C++, thus its name, obviously. It contains the standard technique for MHD called constrained transport, which keeps div B 0 exactly to machine precision, which is very, very nice. This new version has mesh refinement and general curvilinear coordinates, which we're going to use for this problem using spherical polar coordinates. It does enable us to do general relativistic calculations in stationary spacetimes. We're not using the GR algorithms here because we're mostly going to focus on regions, say, 10 RG and farther out, where GR really isn't very important. But if you want to go all the way inside the ISCO, then GR is absolutely crucial. And so we're extending the calculations in the future, and I'll tell you a little bit about at the end, to the fully GR regime. Most importantly, it contains these algorithms for radiation MHD, which I'll describe, and a few other bells and whistles that if you're interested about the numerics, you can ask me about later. So, for example, the curvilinear coordinates are important because it allows you to use non-uniform grids in the radial direction and use mesh refinement to resolve the midplane of the equator, where we know for sure there's going to be these small length scales from turbulence. Whereas at the poles, where there's very little matter because angle-into barrier prevents there being much material directly over the pole, you can use lower resolution there. And so this kind of mesh refinement allows you to put the resources where they're needed, and this kind of mesh is precisely what we're using for these calculations. We are able to go all the way to the pole, all the way to the theta equals 0 and theta equals pi. Typically, that involves adding some boundary condition at the pole, or reflecting wall there in most algorithms, but we've been able to develop a technique that is transparent to motion over the pole without any kind of residual. So this is a test problem. We're taking a magnetic field loop and with a constant flow, advecting it through the mesh, even on a spherical polar mesh. So solving a homogeneous advection problem using a spherical polar mesh is typically not a good idea because you have these coordinate singularities. But with the appropriate choice of boundary conditions and the treatment of this polar boundary, you see that the magnetic field loop just advects through there perfectly fine. There's no issues, and so this is quite different than most codes treating these polar boundaries. So there's a lot of technical advances that we are taking advantage of in these calculations. And as an aside, this code's being used for lots of other things. Another problem I'm interested in is planet formation and planet disk interaction problems. And again, with this adaptive mesh refinement, you can take a global model of a protostellar disk in which is embed a planet, and you can zoom in to the gas flow around the planet using mesh refinement. And you can see the emergence of these spiral density waves being produced by the torque of the central star on the circumplanetary accretion disk. And Xiaowan Zhu and I have written a paper which points out that these spiral density waves can be very important for transporting angular momentum in circumplanetary disks, much as the same way they are in binary star systems. The tidal torques from the central object actually induce spiral shocks, which produce accretion. And so, again, this code's been used for lots of different things using these kind of tools. The most important aspect of the code for this talk is the radiation transport algorithm. We're using so-called variable Eddington tensor approach to close the moment equations. That the variable Eddington tensor is the closure relationship between the the radiation pressure and the radiation energy density. But rather than being assumed, it's computed directly from a solution of the time-independent transfer equation. So at every time step, we freeze the flow. We use the density temperature to calculate the radiation field at every grid point and over all angles. We then take quadratures of the radiation field to calculate this 0th and second moment directly, the energy density and pressure directly, and we compute what the relationship is between those things directly. We then plug that into the time-dependent moment equations as our closure, and we integrate the equations for one time step. It works as long as the radiation crossing time is very short compared to the dynamical time in the flow, so that you can consider the flow to be frozen while we do this radiation transport calculation. So it's suitable for non-relativistic problems. It doesn't require any assumption about the closure relationship, so it's much more general than other approaches. But of course, for the black hole accretion problem, at some point, even if it's not general relativistic, it gets to be special relativistic. The flow velocities, orbital velocities are approaching the speed of light. And so this approach isn't going to work because the dynamical times are just as fast as the radiation crossing times. So there, we just bite the bullet. And we, in fact, abandon the radiation moment equation approach. We just simply solve the time-dependent radiation transfer equation. We evolve the specific intensity as one of the dynamical variables. We store it over roughly 80 angles in practice. And so at every grid point, we have a discretized solution for the specific intensity over 80 angles. And we then just calculate the forces and net heating rate on the fluid directly from just an ab initio solution of the transfer equation. It's only possible because the transfer equation is a lot cheaper to solve per grid point than the MHD equations, which are quite expensive in terms of operations. And so we can do 80 angles at every grid point in roughly the same cost as it is to do one MHD time step. And so this method has proved quite suitable and quite feasible, and we're extending it to more general problems with frequency-dependent transport and so on in the future.
Have you gone back and compared the variable Eddington tensor in both parameters?
Yes, and yeah, so for problems which are, and the problem here is that it's not very good for non-relativistic problems because you have to take many time steps to evolve it for an interesting dynamical time in a non-relativistic problem. So, but they do agree in the limits where they should agree. So you can do diffusion problems and you can do shock test problems, as I'll show you in a minute. Exactly. Yes. And so exactly. How do we know? Well, we do problems like this, which are the propagation of radiation-dominated acoustic waves. So there's very few analytic test problems you can use for radiation MHD codes. One of them is linear waves, and it's limited because it's linear waves, so you're not invoking all the nonlinear terms in the equations, but nonetheless it's an analytic solution that you can use as a test. So from the dispersion relation from these waves, you can compute analytically what the phase velocity and damping rate should be, the real and imaginary parts of the frequency, and that's what the different lines are for various radiation to gas pressures. So capital P is the ratio of radiation to gas pressure from 10 to the minus 2 to 100. So you can see what these phase velocities and damping rates do as a function of optical depth per wavelength. And then we do a series of calculations where you set up a radiation acoustic mode, you propagate it on the mesh using periodic boundary conditions, and you simply measure what the phase velocity and damping rate is coming out of the code, and you plot those as stars for various optical depths per wavelength. And you can see excellent agreement between the analytic predictions and the measured values from the code. You can also compute convergence rates. That is, you can just take one parameter value and increase the numerical resolution and see how the error, L1 error, decreases with resolution. And again, you get first and second order convergence in the regimes where you expect it. So that's one very quantitative test. Both versions pass this test very, very well. A nonlinear test, well, they're even harder to find, but recently there's been some semi-analytic solutions presented by Lowry and Edwards for radiation-dominated shocks. So these are calculating the profile of shocks in which radiation plays a very significant component. So for a standard hydrodynamical shock, you may remember that the variables undergo a discontinuous jump at the shock front whose thickness is just a few particle mean free paths wide. There's mediated by the viscosity in the plasma, and so for any realistic calculation that's so small, you can treat it as a discontinuity. But as Almog pointed out, there's various length scales here. There's another length scale. There's a photon mean free path, and that can be much, much longer than the particle mean free path. So when you have a radiation-dominated shock, it can have a resolved substructure because you have photons which can propagate upstream many, many, many particle mean free paths and change the structure. And so this is exactly what's shown here. This is the profile of the gas temperature and radiation temperature for a supersonic flow coming in from the left and leaving on the right. It undergoes a shock. But the gas is being preheated by radiation, which is diffusing upstream. So you see this precursor, a discontinuous jump at the shock front, and then there's a cooling region where the gas is emitting photons that are preheating the gas. The radiation doesn't show this jump nor this overshoot here. So you can see the quite different profiles you get for the gas and radiation temperature for these kind of shocks. Now you can't calculate these profiles analytically, but by just solving the ordinary differential equations with matching conditions at the shock jumps, these authors have presented a set of fiducial models that we can compare against. And so we've done a whole series of calculations at different Mach numbers, red line being the reference solution from the semi-analytic model, the points being the numerical solution, and you can see, of course, excellent agreement everywhere on the mesh. Yes?
Is there an assumption about the photon absorption versus scattering rate that's being made here? Is it sort of the black body at all points?
LTE is assumed, and the opacity is, it's just continuum opacity. Those are the only assumptions. The calculations by Lowry and Edwards are the full transport solution. They're not in any kind of, not in the Eddington approximation or the diffusion approximation. So the only assumptions come into or not even assumptions, they're just the opacity adopted is for just electron scattering only, and the radiation field is assumed to be LTE. There is thermal photons, of course, right? Because they're well, there is absorption and emission, so it's not non-zero. The dominant source opacity, I should say, so there is thermal emission as well and absorption. So yeah, and the main key here is this Eddington tensor I mentioned before. So it's a tensor, has a 3x3 tensor, and so the most interesting component is the XX component, the component which is telling you about the geometry of the radiation field longitudinal upstream of the flow. In a purely diffusion approximation, it would just be a third. So P is 1/3 E. In the diffusion approximation, you can see far upstream and far downstream, it is 1/3. So the radiation field's in the diffusion approximation. But right at the shock front, it's not. In fact, it not only exceeds 1/3 where the radiation is streaming upstream, it also is less than 1/3 right at the shock front itself. So the point is that any ansatz about the Eddington tensor, which bounds it between 1/3 and 1, must be wrong, because there are certainly geometries you can consider where this component of the Eddington tensor is less than 1/3. And so this is right away, you know you're not going to get the structure of these shocks right if you make certain kinds of closures as are done that limit the value of the Eddington tensor. It's why you have to compute it self-consistently. You really can't just assume it. You have to compute it, because you really don't know what its profile is. It's given self-consistently by the structure of the flow itself. So I won't say much more, but suffice to say there's a whole series of quantitative tests we've tried to do. Another feature of the method that's important is its explicit integration methods make it very, very scalable. So we worked very hard to make this new version of Athena very, very efficient, using standard vector operations on current processors. So right now it runs about 1/20th of the performance of a hand-tuned GPU code, which implements the same MHD algorithm. That's per core, however. Since current CPUs have 14 cores on them, we are within a factor of 2 of a GPU just on one CPU on the processor. And so this, if you really exploit the performance available on CPUs by taking care to optimize it, you can get extremely high performance on existing CPUs and still have the portability that comes with just sticking to the CPUs. And then the weak scaling is also excellent. So this is the performance per node measured in zone updates per CPU second versus number of nodes, out to a total of 1 million processors here. So the largest machine we've run on has had 1 million processors on it. And what you want to see here, of course, are flat lines. You don't want to see the efficiency drop in any way. And you can see that these lines are all flat to within 1.5%. That is to say, the performance per node on 1 million cores is within 1% of the performance on one node. And so we can scale to very, very large numbers of processors and be able to exploit those architectures very, very well, mostly because it's just explicit update algorithms. So let me turn to some of the science results. Let me talk first about these thermal instability results, which are now almost 5 years old. We're going to use shearing box simulations to explore thermal instability in 2 regimes in an accretion disk. An inner region A, where the gas pressure is less than the radiation pressure, and an outer region B, where the reverse is true. The gas pressure dominates over radiation pressure. And here, electron scattering dominates in the inner regions and free in the outer parts. And we're going to do these local shearing box simulations with appropriate boundary conditions. They're going to be very tall, so they capture the photosphere of the disk. So photons can stream away above the photosphere, and energy is lost to the top and the bottom through the emission of radiation. And this energy is coming from dissipation of turbulence driven by the MRI in the midplane. And we're going to self-consistently follow how energy generated in the midplane is diffusing to the surface and being radiated away. We'll calculate the structure and dynamics of these radiation-dominated disks self-consistently. And if you wanted to know, for example, for a stellar mass black hole, what these regions A and B correspond to, so for typical 6.6 solar mass black hole numbers that we took from Turner and Hirose et al. Previous work on this problem, then the region we're considering is about 30 RG, which justifies our lack of GR here. We're well outside regions where GR is very important. Temperatures are 24 million degrees Kelvin. So again, justifying ideal MHD, everything's fully ionized at that temperature. If you're doing region B farther out, that's more like 300 RG, and temperatures have dropped to a mere 3 million degrees Kelvin. Again, assumption of full ionization is very, very good there. So what happens when you do these shearing box calculations? Well, a nice way to show the result are these so-called space-time diagrams, in which case you average the data in horizontal planes at every time step, giving you a one-dimensional vertical profile of the horizontally averaged quantity. And then you plot that one-dimensional vertical profile versus time. Gives you a space-time plot of the vertical profile. So here for density, you can see that while there's fluctuations every 5 or 10 orbits or so, the density is remaining mostly stationary. It's not really changing very much. It's not getting thicker or thinner. There's this very interesting dynamo being driven in the toroidal magnetic field, By. This is a so-called butterfly diagram, which is seen in all local stratified shearing box simulations of the MRI. It's got nothing to do with radiation physics. It's not very well understood, but we know the MRI drives this mean dynamo, generating mean By, and that's what's producing the fluctuations in the density. The white line, which I'm sure you can barely see, is the photosphere, which is well inside the box. And so we have this consistent solution. And for as long as you care to integrate it, it just turbulence and cooling, and it doesn't change very much. So when you take volume average values, there's fluctuations in time, but they don't run away. They don't increase or decrease. There's fluctuations due to the turbulence, but nothing secularly changes. So that's for the region B, the gas pressure dominant case. When you do region A, the radiation pressure dominant case, you see something totally different. The disk is secularly heating up in time. Eventually, the photosphere hits the top and bottom of the box. We tried doubling the box size. It just keeps running away until it hits the top and bottom of that. We can't afford to keep going forever, and so after a couple of times, we gave up. And it also depends on how you start the calculation. It doesn't always run away heating up. Sometimes it just collapses to a very, very thin disk after about 20 or 30 orbits or one thermal time or so. You still see this dynamo acting, but its properties are changing as the disk thickness changes. So the dynamo is still there, but it's doing something different now. The turbulence is doing something different. The thermodynamics is behaving differently. And if you plot volume average quantities, now they are running away. You see the radiation energy density increases by more than an order of magnitude over the time that we integrated this for.
So there's no mean magnetic field?
No mean magnetic field in these calculations. That's correct.
Why did previous people get different results?
Yes, that's the $64,000 question. We did a lot of work with trying to compare results, and I think there's two answers to that question. One is that your algorithm does matter. They were using flux emitter diffusion. This is this full transport method. That actually makes a difference. So if you take exactly the same conditions, exactly the same resolution, and you do a calculation with these two methods. So we did this within Athena. So we implemented flux emitter diffusion. We ran flux emitter diffusion. We get a different answer than when we run these transport methods. The second answer is that to save time, previous groups had used a very, very small box, only a quarter of a scale height wide. And you know that we know the MRI saturates at scales of order the scale height. So they weren't capturing the largest scales, the most important energy carrying scales in the turbulence in such thin boxes. So if you just take their calculations with their code, increase the width of the box, their code, it was Zeus actually, developed by Neil Turner with a flux emitter diffusion module that Neil Turner wrote for this when he was a postdoc at Maryland. So when you do that, you also change the results significantly. So it was those two. Then it runs away in their case as well. Exactly. So we have this thermal runaway. So sure, it looks like thermal instability. That is, the most important criteria for thermal instability, the most basic criteria, is that the change in the heating rate Q plus with total pressure has to be faster than the change of cooling rate Q minus with total pressure. Heating due to dissipation of turbulence, cooling due to emission of photons. If that's true, then when you heat up the gas a little bit, the heating rate will go up more than the cooling rate, so you're going to heat it up even more, and that'll just run away because of this difference. And conversely, if you cool down the disk a little bit, the cooling rate will will increase more than the heating rate will go down. So then it's going to run away the other way. Yes.
So, are you worried at all that you don't have effective cooling like you would have in a global simulation?
So it's definitely true that global calculations could be very different, because not only do we not have advective cooling, we don't have radiative fluxes of radiation or anything else. However, the initial analysis is a local one for the stability property. So it's fair to ask the question, are disks locally thermally stable or unstable? But you're absolutely right, this may have got nothing to do with global stability, which will still need to be, I think is very, very important actually. And we're still looking into the thermal stability in the global models. Yes. So all we did was calculate this Q plus and Q minus from the calculations. We have full 3D simulations. We know exactly what's going on in the calculation at every good point in time. So we can just calculate or measure what Q plus and Q minus are. We plot them versus the total pressure as which is a proxy for time. And you see that the red curve is the heating rate and the black curve is the cooling rate. They're highly variable in this turbulence, but they have trends that can be fit by power laws. And the power law that fits the heating rate is steeper than the power law that fits the cooling rate. So you satisfy the most basic criteria for thermal instability. Although the slopes of these power laws are very different than what you would predict from Shakir-Senyaev alpha disk theory, nonetheless, they at least satisfy this condition. So is it really this Shakir-Senyaev 76 thermal instability? I would say not, because First of all, the disk is turbulent, and you can't really look at thermal, linear thermal stability properties when you have this turbulent flow in which you have nonlinear fluctuations in density, temperature, and every other variable. Most importantly, stress is not directly proportional to pressure, which is the alpha ansatz. Even more important, the vertical distribution of dissipation is not proportional to density. In the alpha model, all of the energy is dissipated at the midplane and proportional to density, with less in the surface layers, which completely determines the structure of the disk. That's not true with MRI. The dissipation does not follow density, and that changes the vertical structure of the disk. So in fact, we think the physics of this runaway is quite different. And there's been a recent paper by Henrik Lader and his collaborators which seemed to produce a model, a stochastic model. Sort of stochastic fluctuations in the turbulence can produce runaway if they're large enough. And that model seems to fit these results very, very well. So it's more kind of a nonlinear stochastic dynamics rather than linear instability as predicted by Shakir-Tsenyaev. But I would say, in fact, local disk models are subject to thermal runaway. I would say that's a solid result, even if it's a slightly different mechanism than the linear instability predicted by Shakir-Tsenyaev in 76. So that's one interesting result. It's also affected by the opacity that you would choose. The calculations I showed before included only electron scattering opacity and are relevant for X-ray binary disks, where the temperatures are so high, everything is completely ionized. But at the temperatures of AGN accretion disks, they're only a few 100,000 degrees Kelvin. And you still have some highly ionized species of iron left around. And iron is unique in having so many transitions, so many bound-bound and bound-free transitions, that this forest of lines ends up adding significantly to the continuum opacity, so-called iron opacity bump. So if you just take opal opacities and you add this iron opacity bump to the electron scattering opacity, you get these curves here, which depend on the density of the plasma, but the bump is occurring at a few times 10 to the 5 degrees Kelvin. So if we stick this opacity table into our calculations, and we focus on a parameter regime where the temperatures are in this 10 to the 5 degree Kelvin, appropriate for AGN disks, what happens? The disk becomes thermally stable. The exact same calculation with the same radiation gas pressure is now thermally stable. And so this is again showing the radiation transport is absolutely crucial here and determines the physics. And why is it stable? It's because you have a thermostat in this opacity law. If you heat the gas up a little bit, the opacity goes down and allows it to cool. And so that's a thermostat. And if the temperature goes down a little bit, the opacity goes up, and so that traps the heat and it warms back up again. It only works on this side of the opacity law, of course. So there's only going to be an annulus where the disk is in the right temperature region where this is going to work. In other regions, it still may be thermally unstable. This gets back to, again, the importance of doing the global calculation to know how all these different annuli are going to interact. So that's one result on thermal instability. More recent work has been on accretion disk corona. Where again, just to remind you, if you look at the spectrum of black hole accretion disks, they ubiquitously show various components. A thermal component from an accretion disk, a thin accretion disk. You see a non-thermal tail at high energies due to a corona, thought to be very, very hot, million-degree gas, 10 million-degree gas above the disk. And you can even measure or find evidence for the reflection of those high-energy photons off the surface of the disk that come back to give you a reflection bump at certain wavelengths. So this model of an accretion disk with a hot non-thermal emission above and below is being very well established. The question is, where does all this incredibly hot gas above and below the disk come from? Where do you get this plasma above the disk midplane that can Compton scatter, inverse Compton scatter seed photons from the disk to high energies to give you this spectrum? And there's been, of course, a lot of work and a lot of ideas. And we just wanted to point out there's yet one more way to do it, which is produced by the MRI just sort of automatically. And that's, again, dissipation is not proportional to density. So in fact, this is a plot of the dissipation, this solid red line, versus scale height in the disk. Here's the disk midplane at 0. The dissipation is actually a minimum at the center, and it peaks a couple of scale heights off the midplane. Again, this is ubiquitously seen in all vertically stratified simulations of the MRI, which means that if the photosphere of the disk is well above this, you won't notice this effect. But if the photosphere of the disk drops below this peak, you're going to be heating the gas where it's optically thin. It will not be able to cool, and it's going to get extremely hot. That is, you're going to be pumping a lot of energy in from the dissipation. It's going to have no way to cool because it can't emit photons. It's going to get really, really hot. And so, indeed, if you just decrease the surface density of these shearing box stratified simulations, decrease the surface density so that the photosphere drops below this peak dissipation region, that's precisely what you happen. Here's the space-time plots of the density showing, again, time-dependent but relatively stationary structures. But notice the temperature now. You get these huge peaks, and in a time average sense, the temperature above 2 scale heights is much, much, much higher than the temperature in the midplane. And that's all caused by these buoyantly rising flux tubes that dissipate their energy off the midplane. They heat up the gas, and the gas is unable to cool, so it forms this very, very, very hot corona. You can see correspondence between these peaks and the sort of most buoyantly rising, strongest flux tubes. So simply having a low surface density disk will give you these corona automatically when you're considering these radiation-dominated systems. So whether this explains all the observations and this is a single mechanism for producing corona, that's not at all clear, but at least it is another route to producing very, very hot gas above the disk.
Systems show clear bistability, right? So there has to be some second parameter.
There has to be more, yes, right. There's other details as well. So let me finish with some of the most recent work, which is doing full global calculations, which are, of course, much more challenging because now we're not just doing a small little box. We're trying to do an entire accretion disk over several decades in radius. So we've gotten a very large allocation of time through the Department of Energy Insight program, which gives open access to some of the DOE's largest computers in the country in the US. This has gotten more than 100 million core hours to run a parameter survey of global radiation-dominated accretion disks using this full time-dependent transport algorithm using 80 angles per grid point, where our mesh spans 3 orders of magnitude in radius, so we're at least 2 orders of magnitude in dynamic range in the disk midplane. Roughly 1,000 cubed resolution for these calculations, so at least 16 grid points per vertical scale height everywhere in the mesh, which is what's required to resolve the MRI. Typically, we run these on about 250,000 cores each, and each calculation runs for maybe 10 million hours. So we've been able to survey a bunch of different mass accretion rates and a bunch of different opacity laws, including both electron scattering opacity only, which is X-ray binary, relevant for X-ray binaries, and also including the iron opacity bump, which is for AGN. And for the same surface density mass accretion rates, you see what a difference it makes. You get much more outflows, as you might expect when you have more opacity when in the AGN case. So we've done this series of calculations. Our allocation's ending in January, and so we're just collecting all the data now, finishing our last runs and going through all the data. It's a tremendous amount of data to analyze. So we have our first paper out, and there will be more on these calculations. But let me just give you some highlights of some of the results from some of the first calculations. So first of all, these calculations start with a bound torus of plasma. So this is a poloidal view of the disk. It's got a weak magnetic field initially, so it goes MRI unstable, generates turbulence, and you get this inflow of matter, and you see the outflow of matter at higher latitudes, in part driven by MHD, in part driven by the radiation field. And a top-down view shows this initial donut of plasma quickly fills in as the accretion in the interior region starts going, and then it becomes highly fluctuating turbulence as you continue to run the calculation. So we start from this initial condition, and we let the disk form self-consistently, and then we measure the properties of the disk after many, many viscous times, or a few viscous times. And what happens is we generate super Eddington accretion rates. That is, if we measure the mass accretion rate through the inner boundary of the box, and we scale it according to the Eddington luminosity, and we use an efficiency of 10%, which is the standard assumed in the field, then our mass accretion rate is 10 to 30 times the Eddington rate. It starts off 0 as the torus gets unstable, quickly fills in, and then there's this highly fluctuating turbulence-dominated regime where the time average mass accretion rate is tens of the Eddington rate. So we're getting these super Eddington accretion rates. And what are the properties of the disk? Well, one of the most important properties is that the efficiency of the radiation transport remains a few percent, 5% or so. And in fact, radiation transport by turbulence is the most important mechanism for cooling the disk. That is to say, there's this interesting dynamical connection between the turbulent motions and the radiation field. Magnetic buoyancy in the disk produces vertical motion. You have turbulence in the MRI, you generate magnetic field fluctuations, they're buoyant, they tend to rise out of the disk. Those correlations are seen easily by plotting the cross-correlation function between density and magnetic energy. And you see that there's a strong anti-correlation. That is, where the magnetic field is strong, the density is low. So these magnetically dominated bubbles have low density, and therefore they're buoyant. So you see the evidence for them everywhere in the disk. More interestingly is that there's also a correlation between the vertical velocity produced by these rising bubbles and the energy density, radiation energy density. That means that there's a net transport of energy by VZER. There's a correlation between these fluctuations so that you get net cooling of the disk. More radiation is being carried out than is being brought back in. Why? Because these low density bubbles have lower optical depth. They fill it with radiation. They get carried up to the surface. Then the radiation gets to the photosphere and can escape. And so you end up having turbulent transport of radiation energy density, which reduces the scale height of the disk, increases the efficiency and luminosity, and decreases the so-called photon trapping radius. So there are analytic models, so-called slim disk models for disks in this regime, but they only include radiative diffusion as a cooling mechanism. It turns out that this advection process can be even more important than that, and it changes the model. If you just include that in the model, you would have a model which matches these calculations much better. So that's one important sort of interesting physics result that's emerged from the calculation. And finally, I promised that we were trying to compare to data, and we've made an attempt at that by taking a snapshot of the calculation at late time. So here's the mass density and radiation energy density at some late time in one of our calculations. We then fed that into a Monte Carlo code to compute the spectrum. There we do full frequency-dependent transport using the temperatures and densities that come from the simulation. We then do a full Monte Carlo radiation transport. And then we feed that into the XSpec package to get the response of various detectors. And we compute the broadband spectra as might be observed by NuSTAR and XMM. And those are these colored lines. So the inner regions give you this blue part, and the outer regions give you the green, high energy tails with this very, very broadband high energy tail. And the wiggly line is actual data coming from observations of what we know to be an ultraluminous X-ray source, therefore super Eddington accretion flow. Therefore, it corresponds to exactly the systems we're modeling. The so-called NGC 1313X1 is one of these ultraluminous X-ray sources. And you get a very, very, very good fit to the data. And there's really no free parameter here except the vertical normalization. We don't know what m times m dot is, because we don't know the mass of the black hole in this case. We don't know what its accretion rate is. But if we normalize this curve to our simulated spectra to fit the data, this is the fit we get. And the product of m dot we need to make that fit work is very, very suggestive. It's a few solar mass black hole accreting at about a couple of times Eddington. So that works extremely well, it seems. And so that's very, very promising. According to this is work that Shane Davis and Matt Middleton have done, especially Matt has been instrumental in making these spectral fits. And it's actually quite difficult, according to Matt, to fit these high energy tails through other models. And so this looks very promising, where right out of the box, we really didn't do anything. We just gave him the data. He did the calculation. It fit extremely well. That's very promising to fitting more sources. So we're now putting more effort to try to compute more spectra of our models and compare to data. So let me conclude with some future work. I mentioned we have this GRMHD working in the code now using stationary spacetimes. We're using more sophisticated Riemann solvers compared to the standards used in most GR codes. Maybe the best known code around is HARM, which uses a so-called local Lax-Friedrichs method, very diffusive Riemann solver. And so you can get order of magnitude less diffusion as measured by, for example, linear waves when you're using these more advanced HLD type solvers for relativistic flows. We've started doing 3D GR-MHD calculations of accretion around spinning black holes. This is something my former student Chris White has been doing, and there'll be more coming soon. We've also been extending these methods to so-called higher order finite volume methods, techniques I've been describing. Like almost every shock capturing code in astrophysics is second order, but we've been, with my applied math student Kyle Falker, he's implemented a fourth order method based on techniques developed by Phil Colella. These look very, very promising in that they indeed show true fourth order convergence for smooth problems. So again, this is a linear wave convergence test, error versus resolution, and you get fourth order convergence for the L1 errors, but it also substantially reduces the advection error, even for discontinuous solutions, which are always going to be first order. You can never be better than first order when you have shocks and discontinuities, but it still greatly reduces the advection errors for this slotted cylinder advection test. So we're exploring the use of these methods for exactly the same problems. They're much more expensive, but since they're more accurate, they end up maybe being more cost beneficial, and that's something we're looking into right now. So I'll just summarize by saying we're able now to do direct ab initio simulations of black hole accretion flows, including a full ab initio treatment of radiation transport. And there's many problems or many systems to which we can apply this: X-ray binaries, ultraluminous X-ray sources, and the growth of black holes in the early universe. It requires an extension of our existing MHD algorithms to do radiation transport, but we feel like that's proceeded a lot. And so we have showed you some work in thermal stability, corona, turbulent convection. We're not the only group doing this. There's many other groups taking different approaches. This is all very healthy because I think cross-comparison between our results is crucial for validating what's robust and what's affected by the numerics. And so I think in the next 5 years, you're going to see a lot more results in radiation, magnetohydrodynamics, calculations in astrophysics, because I think these techniques now are becoming mature enough to be used in lots of different kinds of problems. And with that, I will quit.
Any questions?
So I'm wondering about what happens in the zoom instability in what we call region A.
Yes.
So I wonder, you get the same stability if you run an adiabatic simulation without radiation, but assuming that the adiabatic index is 4/3 instead of 5/3.
No, I don't think that's ever been seen.
So in your super Eddington accretion problem, what's the kinetic energy of the outcome?
So yes, the rate of efficiency is a few percent. So even though we're generating 20 to 30 m-dot Eddington, you're only getting out roughly Eddington in radiation. And the kinetic energy is a smaller fraction of that. So I forget the exact number, but it's sort of a half or a tenth or something like that of Eddington coming out. And it's a very broad wind. It's not a highly collimated outflow. It tends to come out sort of at 45 degrees or so. The radiation field is beamed, but only weakly so as well. It's not pencil beam. It's slightly beamed towards the equator or towards the pole, but not very much.
So it's still very interesting for feedback.
It's definitely interesting for feedback. One of the new runs we've been able to do has gone up to like 1,000 m-dot Eddington. There, the rate of efficiency has dropped substantially. So now it's still hovering around Eddington. So the concern always has been, well, we don't observe any AGN with Eddington ratios that are much above 1. So where are they all? It may be that m-dot Eddington can be much bigger than 1, and you still only ever get out m-dot Eddington from the dynamics.
Does the kinetic luminosity go significantly above LA?
In that case, again, I can't remember the exact number. I think my answer is no, that even the kinetic luminosity has not gotten. So they sort of go hand in hand. So whatever the rate of luminosity is, the kinetic luminosity is not that much different.
You do get most of that luminosity going towards it to accrete.
Yes, exactly. So the vast majority of the material is going in the hole, and the small fractions coming out in the wind with an energy that's sort of order Eddington.
I don't know if I caught whether you mentioned or not. Do you see any signature of the local thermal instability in the global simulation?
Yeah, excellent question. And the answer is no. So we've been looking hard for it because we expect it to be there. But we're able to run these global calculations for about 4 or 5 thermal times, and we've never seen any runaway at any annulus. Why not? Well, I think the simplest answer is global effects, that you have radial transport of mass, momentum, and energy, and that is affecting the local stability. Or it could just be that this is still settling down. You know, a few thermal times is really not that very long. I mean, we want to do thousands, millions. That's going to be very, very challenging. You know, maybe it settles down to some other state that does go thermally unstable. That's a question that's very hard to answer. But my gut feeling is that as soon as you add global effects, this thermal instability, I mean, a simple argument is that, well, if this local patch starts running away, why doesn't it just radiate radially, cool down by radial fluxes, and then that'll suppress the instability? The local assumption assumes the entire disk behaves uniformly. That's impossible because the timescales are very, very different in the inner part and the outer part. So the disk can't respond uniformly everywhere. So if you're going to get little patches going unstable, I think it's pretty easy for it to just, you know, cool itself down locally and shut off the instability. So that's my guess. It remains to be firmly fixed. Yeah.
For the grid in your disk, what sort of refinement criteria do you use, particularly with regards to the radiation, and particularly towards the inside of the disk?
Right. So these calculations use a so-called static mesh refinement. That is, we don't adaptively change it as the calculation's running. That's just because we happen to know that the disk midplane is always going to be in the same location, and we're more interested in length scales at the inner edge than the outer edge. So we use, I think, 4 levels of refinement. So an order of magnitude, roughly, change in the resolution between the midplane and, you know, towards the poles. And we first ran a calculation on a uniform mesh, sort of measured the density contours, and then went back and laid down a static mesh to sort of capture 2 scale heights at the highest resolution, and then the 3rd scale height at lower, and the 4th at even lower. So we adaptively, you know, by hand, put in the static mesh so that we'd be able to resolve what we knew was going to come out in the final evolution.
So, in the HN case, the iron bumps, are you worried at all about the on shifting, which is very significant?
Right. So we do worry about, so the iron opacity bump, I don't think I worry about having to treat the line opacities directly because there's such a forest of lines. The spacing between lines is very small compared, or much smaller than the UV case where you get line driving. So the spacing between lines is so small, you know, you can treat it more as a line blanketed problem where everything is treated by mean opacity. However, you know, at larger annuli, as you know, you should get lower temperatures, more UV emission. You should be seeing very, very strong radiative forces due to line driving, due to, you know, UV absorption lines in calcium-4 or carbon-4 and other species. And there, it is truly a line transport problem. If you wanted to do that ab initio, I think it's just impossible because you have to resolve the line width as well as do the full kinematics of the flow, which means your frequency spacing is impossibly high unless you have very smart adaptive algorithms for frequency-dependent transport. In other words, the problem I don't think has been solved for the star case. So how are we going to do it for disks with a turbulent flow? So the best we can do in that case is adopt CITA formalism, for example, which isn't correct because it assumes a monotonic velocity profile along the line of sight, which these are turbulent flows. So whether or not you can do better than that is a research problem in and of itself. In other words, can you build an accurate treatment of line forces in turbulent flows that extends CAK to multi-dimensions? That's a research problem in and of itself. Doing the direct ab initio line transport problem is going to be, I think, just impossible.